All right, guys, that's how science goes. But the thing is that we finally, after the trial and error and controlling for variables and everything, we got it right. Although there is one thing I overlooked, but I'm not worried about it. Here's the main thing with this conclusion and epilogue. We have, based on the evidence that we gathered, remember with an experiment we need controls, we need reproducibility, we need biological relevance won't apply to this, but we need mechanism. We didn't cover mechanism, but that is the conclusion. We do have mechanism as a result of those experiments, believe it or not. We can definitively say how this O2 sensor works, but we did the controls. The reproducibility, not an issue. I've reproduced this many times with many varying degrees of the amount of noble gas I've introduced. We inadvertently introduced 2 noble gases, so we had reproducibility there, which wasn't even necessary. Obviously, we should do this on other cars, I suppose, but O2 sensors are O2 sensors. So the only thing is the mechanism. Here's the conclusion to the experiment. There is no other possible explanation, and that is I've traditionally thought that the O2 sensor only measured oxygen and hydrocarbon was not a factor. It only measured oxygen. That is incorrect. So I am changing my thinking a little bit, but it's not to the thinking that it only measures hydrocarbon, because that also would be incorrect. The only explanation is that an O2 sensor works by looking at the proportion of oxygen to hydrocarbon and then reacting when that proportion is disturbed. When there is an imbalance in that proportion, it reacts rich or lean accordingly, but it needs both. That is the conclusion. That is how it works. Now, that said, there is only one thing that would disrupt this conclusion. And if it disrupts this conclusion, it disrupts logic and reason as well, because that is the only explanation based on this data we have. So even if you didn't understand the experiments and what we did, this is our foundation. The one thing that could screw this up is with sensor 2. If the post-cat sensor does not stay rich, to be honest with you, I'm going to change careers, because that would be totally illogical. Now, I'll let you guys think about that on your own, because some of you guys are like, what does that have to do with the price of milk? But if you understand what's going on, you will be thinking, oh my gosh, that's absolutely brilliant. But it's key. And don't worry, of course, I'm going to explain why that is necessary. So the first thing that I have to do, we have one more experiment to do. We're going to have to repeat this experiment, but also look at the post-cat sensor and make sure that while there's no change in the front oxygen sensor, that it maintains its stoichiometric path, that we do not get a change in the rear sensor. If we get a change in the rear sensor, we see it go lean, that'll be the end of this channel, to be honest with you, because there's no point in doing logic and reason. So let's make sure that happens, and then I will explain, if you're not following, why that is so critical. To be honest with you, it should be a concern for you that the rear sensor would stay rich, to be honest, if you really think about it. But that is explained by the fact that the O2 sensor works by measuring the proportions. So I'm not worried about that. It'll all make sense in a minute, but first of all, let's make sure the Earth isn't going to blow up tomorrow. Okay, so what we've got here is, of course, our O2 sensor bank 2. And here is our post-cat O2 sensor bank 2. Notice we got good catalytic activity. It's staying rich. And our fuel trim down here. Some people wondering why I want the fuel trim. Earlier, of course, it was to help accentuate, to show the change in the O2 sensor reaction. But now I have the fuel trim here as a control. We're expecting to maintain both of these. And of course, the fuel trim is to show that the maintenance of these is not a result of adjustment of the fuel trim, which we know isn't going to happen, but again, it's just a scientific control this time. So the first thing, again, controls are everything to make an experiment. I have to show that I would be capable of leaning this sensor down for this experiment to be valid. So let's go ahead and do that real quick. Let's put a little air in here. We, of course, should get, and we can see we lean it down. So that's good. We see we have reaction. Let's let that stabilize out. Okay, I needed to clear the dead space from the hose. I had forgotten about that, so it leaned out both of our sensors when I started the helium, but We should be good to go now, so let's go ahead, add our helium. And there it goes. We should start seeing a little bit of jerkiness from the sensor because of the mix. And there it is, and we can see that we stay rich on the post-bank sensor. We should give like 1/4 of a second for the gas to reach there, but you see we stay rich, so everything is good. Okay. So that means that we now know 100%. Oops, I should plug this hose up. Well, actually, we're done. I'm just going to turn off the car. But we know now 100% the mechanism of this O2 sensor. So let's go ahead and talk about it. OK, and the good news is that we're going to just be talking about reason and logic a little bit more, which is easier to follow than a lot of the dilution versus proportion versus concentration. I know that when that's not your world, it's a very difficult thing to grasp and comprehend, so I totally understand that. We're going to do a lot less of that now. We don't need it. And, you know, don't worry, I had a whole thing actually planned out where I was going to go and do the Nernst equation and all this stuff, but we don't, you know, it's not true to the channel. I like to take all that very complex stuff and simplify it, and all that stuff isn't really necessary. After this video, you are going to have a complete comprehension of how the O2 sensor actually works. You're going to understand the difference with an O2 sensor versus an air-fuel sensor, because one of the problems is that I'm kind of making it sound like it's an air-fuel sensor. It's different than an air-fuel sensor, and you will see why. It'll all be very clear. But what we're going to do, I think the best way to approach this is let me tell you why, for so many years, up until yesterday, and one day a few days ago, just for a brief period of time, but why I always believed that the O2 sensor was strictly an O2 sensor. It's not because of adding propane, it's not because of inducing a vacuum leak, it's not because of misfire. It has nothing to do with any of those things that I said were common in the arguments. It was for a completely different reason. The reason that I thought that the O2 sensor was strictly an oxygen sensor was because of sensor 2, the post-cat sensor. It stays rich during stoichiometry. That is a conclusive argument that it is not a hydrocarbon sensor, an O2 sensor, at least so I thought. But I was wrong, because there was only one way that wouldn't be true, and it turns out that that one way it wouldn't be true, we have proven is in fact true. So let's understand that, and then everything else will come clear. Okay, so now we're looking post-cat. As you can see, I don't do the artwork for the channel. So this is our post-cat oxygen sensor. Now, let's look at what happens with the cat, okay? So with the cat, we've of course got some hydrocarbons coming in. We've also got some unburned oxygen coming in. And as we know, post-cat, that sensor trace is going to be high at around 800 millivolts, as we saw. Okay? Now, let's leave a little room here because we're going to make some variables. Now, here's the trick, and this is why my belief with the oxygen sensor was so confirmed. What the cat does is the cat converts the hydrocarbons to, of course, CO2 and water. So when this cat does that, it uses oxygen to do it. And I have a video that explains this on my P0420 diagnosis video. But basically, after the cat, we're going to have, of course, a much lower oxygen content. And, of course, a much lower hydrocarbon content. There's more hydrocarbon than there is oxygen, but both of them are much lower. Let's look at this from the perspective of the oxygen sensor is an O2 sensor. The lower oxygen content, of course, means that the O2 sensor will be rich. So that makes total sense. This is what we expect, and this is what I've always used as my foundation and even taught in the video. If the cat is working, you will have a lower O2 concentration. The lower O2 concentration detected by the O2 sensor, high voltage, very simple. Here's the thing though. Let's look at this from the it's a hydrocarbon detector crowd argument. Well, we got a problem. When the oxygen sensor detects the less hydrocarbon, of course, that would mean you would get a lean reading if it only measures hydrocarbon. Uh-oh, that is really hard to explain for the hydrocarbon sensor crowd. And it is because of that that I was convinced that the O2 sensor must read oxygen, because the post-cat sensor reads rich with the reduced volume and concentration, of course, and because it's reduced concentration, because remember, we now introduce, of course, CO2 and, of course, H2O vapor. So we do have a reduced concentration as well, for those of you that follow the concentration thing. But any way you look at it, that is a major problem for the HC sensor crowd, is to explain why it doesn't go lean on the post-cat sensor with good cat activity. Now, there is one and only one explanation that would basically counter that it's an O2 sensor thing, and that is that if the O2 sensor measures the proportion of hydrocarbon to oxygen. But of course, I completely dismissed that because I thought it was strictly an oxygen sensor, and an air fuel sensor is what measures proportion of hydrogen to oxygen. So I completely dismissed that. Well, as we know, without any question from the experiment we did, that's exactly how the oxygen sensor works. So let's go ahead and clarify that, and then we can talk about some things that people may bring up as an argument, but they're easily dismissed. But let's understand how it's a proportion measurement, how that works, how it's different from an air-fuel ratio, because it is different, and hopefully that will convince. But the bottom line is this. The bottom line is, if you think that an oxygen sensor only measures oxygen, like I used to think, you're wrong. It doesn't. But also the same if it only measures HC. It doesn't. It is a proportional tool. Let's look at how it works. Okay, and of course we also will cover why it was so critically important that we find that the post-cat O2 sensor stayed rich. So if that still isn't clear to you, then don't worry, we'll get that covered. But basically what we know, and I have no question about this, is that, again, the oxygen sensor does not only detect oxygen or only detect hydrocarbon, it measures the proportion of both. And it doesn't even measure the proportion of both, it reacts to a proportion. So that means that the way an O2 sensor actually works is like a teeter-totter. Okay, so that on one side of the teeter we've got our hydrocarbons, and on the other side our oxygen. And this teeter-totter is going to be very sensitive. If you just so much as blow on this side, the teeter-totter is just going to sway all the way over. So, and in the middle here, the teeter-totter changes would be shown as an output voltage here. So let's put our output voltage here. Of course, if we're in balance, then of course we are at 0.45 volts. Now, this teeter-totter is so sensitive that if we even just add a couple more molecules on the hydrocarbon side, that teeter-totter is just going to completely go all or none to the rich. There's no in between. There's actually a little bit, and I'll get into that, but that of course is going to put this over to 0.8 volts reading rich. It's what in science we call qualitative, meaning yes or no, one way or the other, but there's no measurement in between. And that's going to make it different because an AFR, an air fuel sensor, is going to be quantitative, meaning that it can measure differences, and we'll get into that. But obviously it works the other way around too. If we were to go ahead and take those two guys back and put them over here, the teeter-totter would switch all the way the other way, and of course our voltage output on our sensor would reduce to 0.1 volts. So that's how it works. Now, it's not quite like that, so let's go ahead and go back to our stoichiometric here. And what a more realistic representation, because remember, an oxygen sensor is a narrowband sensor. So if we've got rich up here and lean down here, the O2 sensor is very much like this. And it has a very narrow spectrum on what it can measure on the rich or lean side. So in other words, if we were to put, let's say we had 1 million, oops, wrong marker. If we were to have 1 million O2 molecules and 1 million hydrocarbon molecules, and let's say that we added just 5 to that million, then what would happen is that would change our balance ever so slightly towards the lean, and we might see like 0.39 here or something. So it could go ever so slightly if we're in that range. Now, we add one more O2 molecule, that's it. That puts our teeter out of that range, and we would just have our all or none response at 0.1 volt reading full lean, because it's like a teeter-totter. So that's kind of more the way to look at it. You can see where you have to have one in order to read the other. So that is how the oxygen sensor works. There's just no way around it. Now, just to clarify, because a lot of people are going to go, well, that's what the air fuel sensor does. It measures the ratio of the oxygen and hydrocarbon. And that's right. But the trick is it measures the ratio. Remember, this is not measuring the ratio. It is just reacting to the ratio and in a qualitative way. An air fuel sensor would look more like this. It's going to have little support springs on it to prevent the teeter-totter from just going all or none one way or the other. And remember, the sensor here has a much broader range of the detection. So if we were to, let's say we add a couple of hydrocarbons here, that would lower our teeter a little bit, and we would see a change in the voltage representative of that. So it would, well, actually, it's an air fuel sensor, so the voltage would go backwards. It would actually lower. And I have a video that explains how air fuel sensors work, and I don't want to confuse you. So what this device is going to have is it's going to have a little microprocessor in here that converts the air fuel ratio voltage to put out an output that is familiar to the oxygen sensor voltage. That's how it works. So we were at 0.45 before. We've increased a little bit. So now, of course, we're going to go richer. So this is going to make our output, say, 0.55 volts. Let's add a couple more. So we add a couple more. We're still in that wide range. So the voltage will be more representative of that, say 0.63 volts now. And you can see that we go down the line. So we get a more accurate measurement of that. It's not like we add just one more and teeter all the way to 0.8. It's going to be representative of the actual measurement of the proportional difference. So that's the way an air fuel sensor is different. It is quantitative as opposed to qualitative with the O2 sensor. Now, there is no question whatsoever that that is actually how the O2 sensor works. The logic based on the data that we got from the experiment is conclusive. Now, there's only one way that it couldn't be true, and that would have been if in the experiment I did at the beginning of the video, we found that S2, the post-cat sensor, this is your flow of exhaust. God, I can't even draw an arrow. This is really pathetic, but that's the direction of your exhaust. Your post-cat sensor, if it did not read rich anymore. Now, why is that critical? Well, let's look at this. So before the cat, we've got our hydrocarbon, and don't forget that our O2 is green and our hydrocarbon is black. And so we've got our balance here now. So of course our O2 sensor front is in stoich and we're happy. Then of course it enters the cat. So after the cat does its job, we of course are going to have quite a bit less hydrocarbon than before, and also considerably less oxygen. There will be more hydrocarbon than oxygen, but there will be quite a bit less of both. Now, of course, it's not comparing to the reading on the front sensor because it's not quantitative. So it's reading to some previous time point, maybe before the cat activity or something like that. But basically, it's going to read that reduction in oxygen. And of course, the lower oxygen, of course, drives your sensor rich as opposed to lean. Okay. And that was the original thinking. But we know that that cannot possibly be true because it has to be measuring the proportion. But here's the thing. If it's measuring the proportion, then basically that means it's taking a sample here, and of course we're going to get a reading something like that. So it's measuring the proportion, even though we have much less volume, much less, and far less concentration, if you're now familiar with those terms. The thing is, it can still measure the proportion of the hydrocarbon to the oxygen. And when it measures that, it of course is going to show rich. And that is the way it works. The thing is that what would happen if I measured the rear sensor, and instead of it being rich, when I entered in the argon, so let's add our argon in here. So we of course dilute both mixes, but equivalently with the argon. That means this is going to be diluted with argon. So that means, of course, and we better put one more O2 in there, that means our sample we'll need a couple more hydrocarbons in there, but our sample is going to look like that. So we've diluted our sample out, but we still have the proportion. I hope you can see that in the camera. I guess I drew that a little small, but we've got 2 hydrocarbons to 1 oxygen representing the hydrocarbon to oxygen in the sample, but of course it's more dilute. But what would have happened if we now look at our sensor 2 and the sensor started going lean? Well, the problem is, we would have no way to explain that. There's no way to explain that. The only way that that could be explained is if we added so much argon, and remember the argon is neutral, so it is not going to be affected by the catalytic converter. And we added so much argon that our sensor only picked up argon, and therefore no chemical activity with the sensor, no voltage. That would be the only way to explain it. And as a matter of fact, at one point during the previous video with the testing, I kind of regret not doing the sensor 2 data. I'm willing to bet that at one point I was putting so much argon in there that I probably actually caused that to happen, that I diluted that exhaust so much with the argon that it probably didn't detect anything. It obviously didn't show up here, but remember after the cat, that it's going to allow the cat to do a lot more activity on that oxygen and hydrocarbon, and I believe I may have caused that. That would be the only way that you would be able to explain this, but as far as for the theory of operation with the sensor, there would be no logical explanation that you could possibly go lean. And of course we didn't. We stayed rich, as we saw. So it goes to show, that's why it was so important. It proves the theory that is how the oxygen sensor works. And remember, in science, when we say theory, it's not a colloquial version of theory where it's like a guess or this is what I think. When we say a theory in science, it means the actual data and evidence and background and logic and reasoning to show that a system works. In other words, it's not a guess on how it works. When we say the theory on how an O2 sensor works, that's how an O2 sensor works. There's no other way. Okay, so that's pretty much it. Like I said, I've changed my thinking. It is definitely not an oxygen sensor, but it's also not a hydrocarbon sensor. It is a proportion detector / reactor. It does not measure the proportion. That's what an AFR does, but that's how it works. Now, the one main question is, how does this change any way that you would approach diagnosis using the oxygen sensor knowing this? And kind of the nice thing about it that's kind of convenient is it doesn't change a thing. If you want to continue to think of the oxygen sensor, if it's easier for you, as strictly an oxygen sensor or strictly a hydrocarbon sensor, you can do that and it will have no effect on your diagnostic ability. The right way to think about it, though, is that if you've got a lean condition, that there's more oxygen than hydrocarbon balance. And if you've got a rich condition, there's more hydrocarbon than oxygen balance. The only way it can maybe come in useful is maybe in a misfire diagnosis, but even then, actually, the original thoughts will still apply. So, really whatever's better for you, but just know that that's definitely how it works. And then you also can get into a little argument, well, is it actually measuring the oxygen against the hydrocarbon, or is it measuring the hydrocarbon against the oxygen? As far as I'm concerned, I'm not interested in that debate. My thinking was that it is strictly an oxygen sensor. That is wrong. It is not. And I don't care what it measures against. That is the point. Either way, it's an oxygen sensor / hydrocarbon sensor because it needs both. So the only other thing is you can also start opening your mind a little bit. Any good experiment is going to cause more questions than answers. And there's a few questions you can get. And one of them, several people brought up the idea of conducting this experiment in a sealed environment. And this, of course, your O2 sensor here. And we could do this in a sealed environment. And of course, it's going to have a 4-wire because we need a heated sensor. And the thing is that it's a great idea and it's very, very scientific because we have controlled environment, but it doesn't matter actually if you think about it. It really isn't important because it's not that much different from what we did. So we could carry that out in a controlled environment. It doesn't matter. But there's a couple things that I thought might be kind of curious. What would happen if we put it in a complete vacuum? And there's no oxygen, no hydrocarbon, or the same thing, there was only argon or helium in there. And I'm pretty confident that in this event you would get no voltage because you need the hydrocarbon and oxygen to have the chemical reaction. You certainly need the oxygen, that I know. Remember, that doesn't mean it's an oxygen sensor, it just means that it needs oxygen for the electroconductivity. But even then, I believe you need the hydrocarbon to create that potential. But the thing is that it doesn't tell us anything. It's just kind of a curious thing. It has nothing to do with the argument. You could also do this. What would it read if it was in a 100% oxygen environment with no hydrocarbon? You know, again, my guess is that it would probably read 0.1 volt, but this has nothing to do with the argument. These are completely irrelevant experiments that might be applicable if somebody's interested. I am not, but this would not show. If it measured 0.1 volt here, and then I imagine if we had only hydrocarbon, because I believe the oxygen is necessary, I believe that this would read 0 volts. This is not evidence that it's an oxygen sensor. So, you know, it's just important to realize that. And even if this read 1 volt, it read full voltage, because my old thinking used to be that the oxygen inhibited the voltage of the sensor, which is not really true. It still doesn't matter. It doesn't mean it's an oxygen sensor, or it means that it's a hydrocarbon sensor. So all of this is kind of curious stuff, but it's important to realize that when you do an experiment, you need to focus on the one concept you're trying to prove, and all of this is actually irrelevant. All right, well, that is it. Thank you so much. I hope you enjoyed the series. I know some of you guys were really into it like I was, and you start not being able to sleep because you're thinking of oxygen molecules and stuff. And I got to tell you, I think that's awesome. And I'm actually very fortunate because, believe it or not, pretty much every day is like that for me. But it's always with living systems and stuff, which, to be honest with you, I think is actually a lot easier. But you can see how fun this can be, but you can also see that this is real science. This is what science is like. Setting up an experiment sometimes takes many attempts. That's what happens. I changed my theory twice through this, but this is it. I'm definitive on this one, unless some major breakthrough comes through, and I'd have to be very convinced on that. But yeah, science is not just putting a bunch of chum out in the water and watching a great white jump out of the ocean. That's not science. This is, and notice, it's about the thought process. That's what makes this science. You apply this thought process to anything, and that thing becomes scientific. So just always remember that. Thanks very much for watching. Hope you enjoyed it. Next week, we're going to get back to doing regular car stuff. We'll talk to you later.